So continuing our discussion of for the physical layer and defining different terms related to digital modulation, let's talk a little bit about passband transmission. So unlike baseband transmission, which is going to use um, the available signal as is, what we're going to do is we're going to shift the baseband transmission from 0 to some higher number s, so that that signal, instead of going from 0 to b hertz, goes from s to s plus b hertz. And what we're going to do as far as making changes to represent, ones and zeros, or represent bits, is we're going to make changes to the carrier signal that sits in that particular passband. So imagine you can have different signals with different frequencies where S is a different value. And what we're going to do on each of those frequencies is we're going to make changes. We're either going to make changes to the amplitude, the frequency, or the phase of the carrier signal. So in amplitude shift keying, you use two different amplitudes to represent 0 and 1. In frequency shift keying, you're going to have two different frequencies. One of each is going to represent 0 and 1. And as you can see, it's going to be very easy to have additional bits in your symbol using these methods. And the same thing here with, with the phase shift keying, you can only have one, but you can change the phase shift, so you can have that as well. So in the phase shift keying, nominally you shift the phase either 0 to 1 or 180 degrees for each symbol period. And like we're going to see in a few slides, you can combine these methods. So you can have a very complex symbol with multiple bits. So here's our basic look at passband transmission. So we have a very simple diagram. So we start off with a digital signal, which is a 0 followed by a 1, followed by a 0, followed by two ones, etc., etc. And we're going to take our carrier signal and we're going to make changes to that signal based on whether we have a 0 or a 1. So in the this example here, we're making changes to the amplitude, whether we have a 0 or a 1. In this next one, you can see the frequency of the signal changes, where the frequency is higher for a 1, lower for a 0. And on this last example, you can see there is a phase change. So you can see when you have two zeros together, they're in phase, and then when we transition to a 1, it goes out of phase, and then it changes to the previous phase after that. So those are the basics of passband transmission, which we can add to that. And some of the ways that we can add to that is, say, for example, if you look at our phased shift keying, so just kind of go back over here for a second. So we said the phase shift keying, we shift 0 or 180 degrees. But let's say instead of doing that, you had 4 shifts to 45, 315, 225, and 315 degrees. This lets you transmit 2 bits of information per symbol. So this could represent 0, this could represent 1, this could represent 2, this could represent the number 3. So basically 2 bits of information per symbol, and we have an example of that. We call that a constellation diagram. Now if we take that and we build upon that by combining a phase modulation with an amplitude modulation, we have what's called a quadrature amplitude modulation. So there's some examples on the next slide. The first one shows 16 combinations of amplitude and phase, and the third one shows 64 combinations. So if you look at the drawing, and we'll look at it in a second, you're going to see that the phase of a dot is indicated by the angle line, angle line from the origin. A line makes from the origin from it to the origin, makes with the positive x-axis, and the amplitude is the distance. So the phase is the angle to the dot, and the amplitude is the distance. And we see this example. So this is a first example where we just have our 4 phases, so we can represent 2 bits. In the second one, each dot represents different angles. Well, these two are at the same angle. This is at a different angle. So these guys are the same phase but different amplitude. So every location on this axis, like I said, the angle represents the phase, and the distance represents the amplitude. And so you can see by doing this, we can have very, very complex bit structure being sent across an analog signal, so we can get a lot of data passed without having too high of a frequency symbol, and we can get a lot of signal, and we can get a lot of data passed through the available bandwidth. And this kind of shows you why over time we've been able to increase, one of the reasons we've been able to increase how many bits per second we can send through a media, even with the physical limitations of that particular media. We've been able to do, by doing mechanisms like this, we're able to increase our data efficiency. Next, we're going to talk a little about frequency division multiplexing, time division multiplexing, and code division multiplexing. So imagine if you have that signal, you've done all those things with amplitude and phase shifting, and you have each of those guys on. You're doing that at a particular frequency level. Now imagine if the frequency you're using is a subset of the overall bandwidth of the medium that you're using. What you can do is you can take that bandwidth and you can divide it up into subfrequencies where each subfrequency is dedicated to a particular user. So this allows you to divide the spectrum into frequency bands with each user having exclusive possession of some band in which to send their signals. And in order to prevent interference, there's usually a guard band that's set up. So maybe if each band is 3,100 hertz, you basically have a width in between each band of 4,000 hertz. So you have some space in between, so the signals there's no crosstalk between the signals. So here you have each channel has their own frequency. So the first one is around up to 64 hertz. This one's up to 68 kilohertz. This is up to 72 kilohertz. So they're all different channels. Like I said, you can be doing amplitude and phase shift keying within each of these channels, so you can be sending multiple bits per symbol. And now you can have multiple users doing that simultaneously on the same medium. Then you have time division multiplexing. Kind of works the same thing. We've already talked about this a little bit in our link layer discussion. So basically, as you divide up the users and give them time so they have the entire bandwidth available to them, but just for some time slot. And just like you have a guard band, you have guard times as well. Another more complex way of dividing up a signal, a carrier signal among users is what's called code division multiplexing. So just to kind of give you a real world example, time division multiplexing, let's say you're at a cocktail party, time division multiplexing is basically kind of everyone taking turns to talk. If you have a bunch of people in a room talking, if each person takes turns. Frequency would be almost like different people are talking in a different pitch or different tone, so you can differentiate the voice of the person you're talking to versus the voice of somebody else. Code division multiplexing is being in a room where there's a bunch of people talking, but you and some other person can speak to each other without being distracted by other people because the other folks are speaking English and you're speaking French. So that's kind of what code division multiplexing is like. So you're sending different signals, and they can transmit over the entire frequency spectrum. They're not taking turns, but the transmissions are separated using coding theory. So we kind of take advantage of some binary mathematical characteristics to make this work. So imagine for a 1 or a 0, each station or each user sends what's called a chip sequence for 1 and the negation of the sequence for 0. And we'll see an example of this in a few minutes. So the chip sequences are what we call pairwise orthogonal. That means if you take the normalized inner product of any two chip sequences, say like C, S, and T as examples, or our two chip sequences, their normalized inner product is going to be equal to 0. Also, for this to work, the receiver needs to know the sender's chip sequence in advance, and if it receives a sequence S, where sequence S would be a whole bunch of users' overall signal, it can find the value of a particular user, say user C, by computing the normalized inner product of S and C. And we're going to see an example of that in a minute. So here we have an example. We have 4 users that are going to send their signals across a particular station. So we have user A, that's its chip sequence. User B does user B's chip sequence, that's user C's, and user D. And you can see over time you have A sending some zeros and some ones and some a 0 and some ones, and you see B has the same, has its own pattern. C has its own pattern, and D has its own pattern as well. Notice in this particular example over here, I do believe that this is not an error. I believe what this is trying to show is in these time slots that D is not sending anything. So you either have a positive, a negative, positive, symbol or voltage, or negative, or no voltage at all. So the challenge is going to be, we have all these separate signals all sent on a wire together, and we need to find some way to differentiate them at the other end. So we have the signal that C is sending we have the signal of, the first signal we have is SC sending. The next signal that we have is B plus C. The next one we have is A plus the negation of B. And then the next one we have is A plus B plus C, then A plus B plus C plus D, A plus B, the negation of C, and D. So these all get added up together, and basically what we need to do is take the normalized product, and when we do that, we get the correct value of C. By taking the product of the signal that's sent, we're able to filter out the value of C.